So welcome friends today in AI Club this Sunday, and thanks for joining in a Sunday afternoon after lunch. So hopefully I'll try to keep it interesting so that you don't sleep or you don't feel lousy or drowsy, whatever it is called. Okay, so we'll start with a bit of introduction from yesterday's session. So yesterday we were studying recurrent neural networks, part one. So recurrent neural networks, as we discussed yesterday, it is mainly used for processing sequential data. So I gave you enough examples of sequential data like videos, audios, English sentence, English sentence, or sentence in any language, or images to some extent. Image also to some extent, not fully, but to some extent. Then DNA sequences, stock market curves, whatever stock market prices we get in the form of plots, na? So that all is sequential data, right? So sequential means next record depends on the previous records, and not only previous records. It may depend with many previous records, like if video frames are there. So context of this frame can depend upon say 20 previous sentence, 20 previous frames, right? And full sentence. So we are all aware about dependency in sentences. Suppose sentence is having 30 words, one single sentence. So 28th word, the context, to understand that context, you have to see maybe 15 words back, whatever was written that is related to that. So it happens, right? So we know all this dependency, and the dependency can be short or long. Short means immediate past, only one word, only one frame, last frame, that is short dependency. Long dependency means 20 words back, 20 frames back, like that. So many times frame, if we have dependency of many time frames, then it is long dependency. So we understand the difference between short and long dependency. So sequential data is very important in our life because language, speech, or audio, video, whatever you call, so everything is a sequence. So if we can process sequence, it is of immense value in real life. And yesterday we also discussed a couple of reasons why we cannot use ANN or CNN, artificial neural network or convolution neural network, why we cannot use them in processing sequences, right? That's what some reasons were discussed in yesterday's part one lecture. And RNN is and we had to devise special RNN recurrent neural type of networks, which are special networks to process sequences. That's where we were yesterday. So we see unfolded and folded form very easy. Folded is one network at a time. Every column here, if you see X0, A and H0 output, X0 is input, A is the processing unit, and H0 is output. So it's a independent. It's a ANN. It's a neural network in itself. It's a ANN unit in itself. And since we have dependency in the past, so all previous sequences feed into the next sequence. So we now know by this time that how to put in folded form and unfolded form. So these are both folded and unfolded forms. I have given many views. So this is a bit mathematical representation wherein inputs are denoted by Vm in a time step t. Time step t is always given as a superscript. So t minus 1, t plus 1, that these are time. So this time may not be actual time in seconds. It can be it can be like first frame, second frame, time t maybe third frame, time t minus 1 maybe second frame, time t minus 2 maybe first frame, like that it can be. So it may not be necessarily always the second or what we understand as time. Time means some sequence. Either we can number it 1, 2, 3, 4, or we can actually see it in the form of 10 second, 11 second, 12 second, like that. So then HT is your intermediate output, and it gives a output of YT. V is the input and YK is the output. YK is your like time step output. So whatever is shown here is a multi-input, multi-output kind of RNN. So one more, so better representation if I put it like this. X is the more easier for us to understand. X is the input. H is processing happening. Between input and H, which is U is the matrix, weight matrix. It's a vector, okay? It's a weight matrix, and it is called embeddings, weight embeddings or weight matrix between previous input HT minus 1 to HT. Next is HT, previous is HT minus 1. Between that also we have a embedding, weight embedding matrix, which is W, and between HT and output O, again we have a output matrix, which is V. So U, V, W are your weight matrices, which are called weight embeddings, and they are passed down across the networks. As you can see, for every repetition of that ANN in the sequence, it is getting passed down. So now we go to this simple feed-forward equation. So I think we have discussed in enough details yesterday, so I'll not repeat today. The feed-forward equation. Then the last we have deployed softmax. So Malini madam, can you tell me why we have deployed softmax and not a sigmoid? Why we have applied softmax and not a sigmoid?
Because of multiple outputs.
Yeah, multiple outputs. It's a multi-class, na?
Yeah.
So sigmoid does similar job, but only for yes or no. Two. If the classes are two, yes, no, 0, 1 kind of. If you have multiple classes, then you go for sigmoid. So sigmoid is an extended form of softmax is an extended form of sigmoid function. So basically, it will give us. So it is a simple representation in words. I have given you many representations so that any kind of family representation comes in future, we are familiar. So this is how also it is represented. Then we understood we have many architectures of CNN. So it is many to one. So here is a tweet. Movie is good. So we have to classify this tweet whether this tweet is positive or negative. So output will be only one. There are only two classes. Output only one. So in this we'll use sigmoid function. Output is only one, positive or negative, 0 or 1. Inputs are many. So we are classifying. Okay. Then it is many to one. This moving interesting. Same thing represented in a bit expanded format. Same network which is showing here right now is being shown in a bit expanded format here. Then you have many to many here. Many to many inputs, many outputs. So many to many are two types. Number of input features are equal to number of output. That is one type. And second type is number of input features. Output features are not equal to number of input features. So example of such second case is that language. So if I'm putting an English sentence, it may form 10 words. But if I'm getting out translating into French, the output may be only for 8 words for a similar meaning. Okay, so these are two types of many to many, and then then same thing repeated many times for different point of view. And then one is one which is more and very complex. One more is one to many. Like I give any topic, like romantic movies, romance. I give only one word, romance, and you have to make a complete essay out of it. Romance, essay on romance, or so essay on youth. I give only one word, youth. Write an essay on youth. So that is where input is only one word, output are many. So that is one to many, and these are usually very complex type of neural networks, and generally they are not covered in courses like this. GAN, GAN, and all those kind of networks, and generally coding is difficult for them, so we may go for ready-made services which are available. So big company will train such kind of neural network, one to many neural. They will train with millions and millions of record. They will train and they will make it available as a service to us. And we just pay per transaction. Just put one word, deduct some dollars, and get your essay out. So many companies are using it. Actually, I know a few companies who are writing stories with the help of AI. So they are using this kind of GAN. Startups, they are using this kind of GAN kind of networks. but they are not developed by those companies. They are just using those networks. They are users of those networks, one to many networks. So they give words on maybe an advertising. So you have to put one advertising song on a topic. So they will just put one topic name, and they will get some melodious song which can be used in advertising purposes. Or if you have to put some advertising text in, say, a full page advertisement is there in Economic Times, and you want to write a complete text on a subject, some very flashy words and very attractive looking, and it is very good to read and all that. So those kind of applications, people are using services which are developed by these biggies of the world like OpenAI, or there are many other companies which write this kind of services. So they pay per story, maybe one of very cheap actually, $1 to $3 per use. They pay it and they get their story out. And maybe then there is a manual editor, manual intervention. Manual intervention is involved, in which one actual physical writer will be examining that the story is spitted out by your AI network. So he may do some more angles and more minor modification so that it is more interesting to for the context they are using, more interesting to humans, or those if any errors are remaining. But these tools are very sophisticated. Generally, if I give you two story, one written by human and one written by AI, very difficult to classify which is written by human and which is written by AI. So this is one in many, many to one, many to many, many to many, many to many. Two forms are there, so we'll discuss it later. One is encoder decoder, and other is simple many to many. So then we go for then this we gave a class break here yesterday. So till here it was kind of revision, and now we get into our real class 2. So welcome to today's lecture. So I wanted, before we start the class, I wanted to show you a very interesting PPT that I found today on the net while surfing. So this is a encoder decoder type of network. Like you see, there are many inputs. Inputs are x1, x2, and x3. Output are only y1 and y2. So it is a many to many where input doesn't equal output. It is a kind of, so it looks something like this, many to many architecture. And like you are inputting x1, x2, and x3. So somewhere it has to end, right? So how network will understand whether sequence is complete or not? Because loss function is there in the back propagation, no? So that loss is propagated back only when entire sequence is consumed. All the inputs x1, x2, x3, when we completely give, then only they calculate the loss and propagate it backwards after calculating derivatives to update the weights and biases. So for that, complete consumption of sequence is very essential. So how the network will know whether your sentence is having 3 words, 4 words, 5 words? So a simple trick. There is a small word we put BOS. BOS means like your sequence end of the sequence. BOS we put a word BOS, which is end of sequence. So but as soon as the input network encounters that it is end of sequence, then it will start processing it, do back propagation process, and start you giving output. So now back propagation is at the time of training. But actually, when we run the network, that time there is no back propagation because weights and biases are already calculated. But at that time also, we need to tell network that input sequence has ended. And similarly, output like encoding we end with EOS. So BOS, EOS for input, EOS for output. They are for end of sequences. Because how do you know? Network is giving you words like y1, y2. So how do you know whether it is complete or not? So you know because you have encountered the simple word EOS. How network knows that you have completed the input? So it does when it encounters BOS. So I'm not sure whether BOS and EOS are exact words which are given, but some kind of words are given at the end of both input sequence, and network also gives you a end word like which is fixed at the end of your output. So both the time it is given. So for now, let us assume that BOS is the end word for input sequence and EOS is the end word for output sequence. So this is there in the course PPT which I just now shared on our Telegram group. So have a look at, there are many other advanced architectures are given. It's a very good, I think some US university course is there. So done by some professor. So very nice advanced topics are also given. You will at least get the current topics which are under development or which are hot topic. So like see here you can see it's one portion is below is noted as encoding and decoding. So encoding means it will consume your entire input sequence. Decoding means it will give you the output. So it is this kind of RNNs are called encoder decoder type of networks. So it's very interesting. That's why I thought let me discuss this example in the class. So now then we get into little more details of today's topic. So now what I want to discuss is tell you like how Rnn training happens. So yesterday I think we had enough discussion on how training of neural network happens. So let us discuss it one more time quickly. So I'll read one by sentence by word. In training any deep learning network, in training any deep learning model, the loss is computed and back propagated after the entire sequence has been digested by the network. Understood? Like training will begin only when entire input sequence is digested. So that we'll see at the by end of word BOS is come. We'll encounter BOS and then our loss will be calculated and then it will be a derivative will be taken, and to minimize the loss function we'll take a derivative to minimize the loss function, derivative of loss function, take a derivative with respect with weight or bias and equate it to 0. That is how we find minima, right? Those in our college days we used to find minima of a curve. How to find minima of a curve? Derivative of that particular curve is, suppose U-shaped curve is there. So minima is on the bottom of U, right? Bottom of U. So at the bottom of U, the slope, if you put a tangent on the bottom of that U curve, that time that will be parallel to x-axis, right? That if U is kind of vertical, a tangent on the bottom of U will be parallel to x-axis. That means its slope will be 0. That is why our loss function is always a curvature. So we take loss function, derivative of loss function with the help of a trainable parameter. We take W or B, we take a derivative and equate that to 0. Why we equate it to 0? Because at any, if it is a minima, then the slope of that curve has to be 0 at that point. The tangent on the curve should be parallel to x-axis if curve is kind of vertical. Okay, so that's how we equate it to 0. And whatever derivative comes, if that is not 0 means you have a loss. So that loss we calculate backwards. And with that, in that backward propagation process, from one layer to other, layer to other, till we reach the input layer, minimum input layer. So weights are getting updated. Okay. So loss function of RNN depends upon the type of task and architecture. Very fair. Type of loss and in many-to-one architecture, the loss function is simply the difference between predicted and actual level. So this kind of architecture. This is one-to-many, na? So I wanted to show you many-to-one. 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 So second one. Many-to-one is second one actually, second figure. Out of this 4, second figure, many-to-one. So 1 is your output. So it is very easy to calculate loss. How? The predicted value, whatever comes, is either 0 or 1. You compare with the actual level. So if predicted value is 0 and actual level also 0, so you deduct 0 minus 0. So that is loss is 0. You are happy. Your prediction is correct. But predicted value is 0 and actual value is 1. Then your loss is 1, right? Minus 1. So we square it. It is same as gradient descent method of your linear regression. No difference. So just compare predicted value with the output value and square it. So that is how we calculate the loss function. So for many to one, it is very simple. Just compare the output with the predicted value. Sorry, predicted value is your output and compare it with the actual level. So that is our loss. So what happens in case of yeah. So in many to many architectures, the RNN network produces an output multiple times, right? Many to many. Visualize many to many. So there are many outputs, right? For each time step, there is output. So there are many outputs. And the loss is calculated at each time step. Each of your time step is a independent ANN, independent neural network, right? So for each step, we calculate loss. In many to many, the total loss is the sum of the losses at each time step. When entire sequence is consumed, for each time step, whatever is the output we calculate, compare it with the actual level, compute the loss and add it up. So that forms the loss of the entire RNN. Okay. And once you calculate the loss function, entire that lot function, take a derivative of that, take a partial derivative of that, which is with respect to one of the weights and biases. So there will be many weights and many biases, right? So take any one weight, first weight, find a partial derivative of that loss function with the help of with respect to that first weight, and then propagate that loss towards the beginning till the input layer. From output layer till input, you have to propagate, and in this process, your weights are getting updated. Now you will ask me how these weights are getting updated. So I'll say that this process is very complex. We have multiple layers and multiple weights and biases. The process is very complex. It cannot be explained orally and very difficult to express in chalkboard also. So you just case a case of two-layer neural network. Assume there are only 4 weights and 4 biases, two neuron in each. So 2 neuron means 4 weights and 4 biases you have total. So and for that you can manually work out how back propagation works. And as I had promised yesterday, today I have this morning itself I have shared you one example, one article in which that such example is back propagation is they have worked out with the help of numerics, like with the help of integers and numerals. They have worked out simple neural network back propagation, how it works. So I will suggest you have a look at that. So that's how total training of RNN happens. Okay. And one sequence consumption, one sequence output. So that is only one iteration of your loss, back propagation process. So this is repeated with minimum input sequence, like you take millions of millions of sentences you give as input, and for every sentence you calculate feed forward and back forward, back propagation both. So that is one iteration. So that there are thousands and millions of iteration happen before you reach the convergence of a neural network, right? So one sentence input and translated output is your one iteration. Like when you put input, there will be feed forward. When you calculate the output and apply the loss function, back propagation. So one feed forward and one back propagation will be one iteration for one set of input sentence, input words and output words. One set, one iteration. So like that, you will train your neural network with thousands and say millions of sentences before you reach the desired convergence. So what happens at the stage of convergence? When convergence reaches, the weights and biases are saturated. Saturated means if you put 1,000 more sentences for training, they will not get updated. Their value will not change. You have to that time you have to understand that training of my neural network is complete. That means that my weights and biases are saturated. They cannot be updated any further. Okay. So till this time, if you have any question, I think I will welcome questions. Malini Madam, Shailesh.
For this Because it is a it's a repetition of neural networks. So for all these RNNs, all the individual ANNs configurations are standard or not? Means is it standard, or we have to each time we have to set up the number of neurons and activation?
Oh, it depends on the task. Yeah, it depends on the task. So these things will be more clear to you when we will do our numerical examples, our Python examples. Okay. So these questions will be better clear at that time. So let us park it for that time. Okay. So till right now, try to understand what is being taught theoretically. Okay. But architecture of RNN will, of course, depend upon the task which are you are trying to do, many to many, many to one, one to many, like that, right? Okay. So that's how it depends. And when we'll work out numerical example, then you will not ask this question. Okay. Malin, any question till this stage?
Yes, sir. I'm a little unclear about all these one to many, many to one. I have understood with respect to text.
Yeah.
How is it relevant for video? I'm not able to clearly relate.
Video means what?
Like video also will be in a sequence, right? So
what do you mean by video? Full form? Can you tell the full form?
Video.
Oh, video. Sorry, I am understanding video. Okay, video. Okay, yes. So video will be the video. Yeah. So video is a sequence, input sequence. Okay.
Correct. So what kind of
applications it can happen?
I'm not able to clearly relate to that.
See, I'll give you a very simple example, which you will never forget. Like video means you have a 20-second video. So video is nothing but a set of images, right?
Yes, that's correct.
So in 20-second video, you may have say a few hundreds of frames. One frame is one image. And they are in sequence. So they are sequential data. That is sequential data. Now I will give you one example, very practical example. Whether you are working for say YouTube, and YouTube people are you, me, anybody can go and upload video without any editing. Nobody will edit them.
Yeah.
Or there will not be any approval or scrutiny of those videos. As soon as you upload them, they are available for show, right?
Correct.
So now across the globe, 1 million type of people are millions and millions people are of the type of people of different character are uploading videos. So some people might object upload say like objectionable content.
Yeah. So you're telling RNNs can be used to screen that.
Yeah. So if it is an objectionable content, you train your RNN to read that kind of objectionable content.
Oh, okay.
So it will consume that video sequence, and immediately in seconds it will tell before at the time of uploading itself it will sequence, it will process it and tell if whether this video is fit for YouTube loading, yes or no. And it will not tell you the answer. Automatically it will get processed. If it is of objectionable nature, it will not allow to upload.
Okay. So in that case, like this loss function would be taken like at the end of say 20 seconds?
No.
How would it be?
Yeah, loss function will be calculated at the end of 20 seconds.
Okay.
No, see, but you try to understand. When we use RNN, we don't calculate loss function. Understand? Right now, what you are doing at YouTube, you are consuming that 20-second video and just giving output whether the video content is objectionable, yes or no.
I understand that. But what if we were to use these kind of videos for training?
Then at the end of 20 seconds, you will be calculating the loss function. Monetization will happen at the end of complete video is consumed.
Okay, yeah, I get it.
Okay, na?
Yeah.
So that's how it works. And so if you don't have any more questions, we can go ahead. With the help of, in this slide, we are discussing yesterday two interesting problems of gradients, which is vanishing gradient and exploding gradients. I think we discussed it, already discussed it yesterday in very detail. But for sake of completeness, I'll discuss it today. What happens? You have calculated, like you have, say, Malini madam is telling video sequence. So 20 seconds of video sequence is consumed. You are calculating loss function. Calculated. Loss function is done. You have computed the loss function. Now you are taking the derivative of that. Derivative with the help of a weight, existing weight. So that will be a number. Output of a derivative will be number. What we want? That output we want, that derivative we want to be 0. If that derivative is 0, that means we have reached the minimum. Understood, na? We have reached minimum. Now, there are two cases. That derivative is not 0, that is first thing. That derivative can be a positive number or a fraction less than 0. It can be less than 0 or it can be more than 0. It can be 1.25 or it can be 0.25. For example, understood, na? I am finding partial derivative of that loss function with respect to one weight, W1. And ultimately what I will work out, because I have values of everything, it will work out as a number. Now while I am working out mathematics, that time it will be formulas in terms of variable. But when I actually compute that derivative, that will be a number. Understood, na Malini madam? Is this understood, Shailesh?
Yes, sir, this is understood.
So at the time of actual thing, that loss derivative will be a number. So that number is 0 means we have won the war, like it is perfect. Derivative 0 means it is already minima. But if number is not 0 means it can be either greater than 0 or less than 0. Now take the case, first case, whether the derivative which you have calculated with the help of W1, the first trainable parameter weight W. First we have calculated W1 with the help of you computed derivative and it is less than 0. Say 0.25 or 0.35, any number you take. 0.25, 0.35, 0.55, 0.95, 0.99, any number less than 0. Okay, so now any number less than 1, sorry, any number less than 1. So if it is a fraction, actually I have to repeat it. So this derivative, if it is approaching 0, then we are sure that our loss is minimal. So we are okay. So if loss is, then next case is whatever derivative we are calculating, that derivative may be above 1 or below 1. So if it is a fraction, what happens? You are back propagating that fraction of suppose 0.95, suppose is your number which you are getting that derivative with respect of W1, and you are back propagating it. So how you back propagate? So if you see that example, if you have circulated this morning, if you will see that backward also you have to multiply by the, so last layer is suppose 4th layer, and then 3rd layer is having 7 neurons. So 7 neurons means 7 into 1, total 7 weights are there in between. 7 in neuron, first neuron layer weight, first layer neuron and second layer neuron, 7 and 1. So last layer is only 1 neuron, and after that immediate intermediate, after that immediate layer is, inside layer is having 7 neurons. So 7 into 1, total 7 weights are there. So we have a weight matrix of 7. 7 value. So now when you back propagate, you have to multiply your gradient with this weight matrix. And if you multiply with that weight matrix, what will happen? Already your number is 0.99 and you multiply it with a number more than 1. Suppose your weight matrix is more, collectively it is more than 1, or point-wise multiplication you are doing and that particular weight is more than 1. So suppose I multiplied 0.99 with 2. So that number will reduce or increase?
It will reduce.
It will reduce, right? Because you have multiplied. Then whatever resulting number is there, I again multiplied with, for the next layer I have a weight matrix of 20 by 20. 20 by 20, I have a weight matrix of 20 neuron by 7 neuron. Like that I have another weight matrix for one more layer inside. So 4th layer and 1 layer I have done multiplication. Number came 2, it reduced by, 0.99 reduced. Then from 3rd layer to 2nd layer I go and then I have a matrix of say third layer is having 7 neurons, and after that suppose second layer is having 9 neurons. So 9 neuron by 7 neuron weight matrix is there. I again multiply. So it will be a kind of matrix multiplication, right? Matrix multiplication. And suppose weights are more than 1 again, so it will further reduce. So your training is happening, but with each layer back, you are going back by one layer. Your derivative is reducing. And derivative is the number which contributes to your training. You need derivative to be a substantial number, so that your weights and parameters, weights and biases can be updated. Derivative should not vanish. If derivative vanishes, your training will not happen. So till up to say second layer derivative was 0.001, and after that, after the second layer, between second layer and third layer, it became say 0.1001. After 0.10 zeros and then 1, it is very small. Then your training between second layer and first layer will not happen, because your gradient has vanished. Why it vanished? Because initial fourth layer itself, the last layer was fourth layer, so in that fourth layer it was less than 1. And then as you went third layer, second layer, first layer, you multiply it with a positive weight matrix, which is weight matrix numbers which are more than 1. So in such cases, your gradient vanishes from layer to layer to layer as you go backwards. So training, then your training will not happen. Neural network training will not happen for few layers. So we don't want that to happen. So this problem is very common in RNN, because RNN networks are huge. You see there are multiple networks. So there are huge, so many layers. So it's a very like a rampant problem in RNN, and that too when then you have long sequences. If you have say a word with you are giving your input is a word with 30, your sentence with 30 words. Can anybody tell me how many ANNs we are dealing with? Inputs are 30, time steps are 30. Now my simple question is, for the input encoder part, how many ANNs you will deal with?
30.
30, right? Because for each time step you have 1. Now suppose my sentence is having 150 words, then I'll deal with 150 dependent ANNs. So this for long sequences, this vanishing gradient problem is very much acute, and it is very real. So if you use a simple RNN, your gradient will vanish after a few layers, or after a few ANNs it will vanish, and then training will not happen. So your purpose is not solved. You are not given the solution of that problem, right?
Sir, so this brings me to one question related to the architecture of RNN.
Yeah.
How do they design? Like I know that I want to build an RNN for sentiment analysis example.
Yeah.
So do we take an example of we read?
Same. Word.
We read a sentence which has probably 20 words in it. We take that as an average and build our RNN based on that, or how do we do?
Yeah, what we do, suppose we are dealing with say 1000 tweets as inputs. 1000 is very less number, but I'm taking an example. 1000 tweets are available for input. Okay. So we take a word bag of it, like you to find out, we remove word like is, a, are, then, them, like that. Though these are conjunction word, connecting words, we remove them.
Okay.
And we create a bag of words. We combine all the 1000 tweets, and after removing is, n, a, are, those kind of words are there, na, which doesn't make any sense. They are just connecting sentences. Those kind of words we remove. And after that, for combining 1000 tweets, we will have a bag of words, right? A bag of words will be there.
Okay.
Those bag of words may have say 1000 sentences you have, and suppose all unique words will take. So unique words may be say 6000.
Okay.
Unique words are 6000. So we design a RNN with 6000 vector input vector.
Okay.
So these are very basics of natural language processing, which will become very easy to you, like when you will read or when you will learn natural language processing, na?
Yeah.
This kind of preparing bag of words, unique words, removing is, a, n, those kind of words. So that comes under data preprocessing. It is a part of data preprocessing. Okay.
Vanishing gradient problem. When we discussed about ANN, there also we especially
It is
with
same
sigmoid
thing. It is
function.
same thing. It is same thing. Same
Yeah,
vanishing
so
gradient problem.
there we in sigmoid function when we were discussing, it was a problem, right? At the end, it was having some vertical or horizontal thing which is parallel to the axis, right? So
Yeah.
there we replaced the activation function to the I think 10H or something, no? But so can't we follow the same thing?
In ANN, we have replaced it with ReLU. We say ReLU solves this problem.
Sorry.
ReLU solves this problem. But here we don't do that because that is not effective. And here we have two tricks which you are going to learn here, which is two neurons, our neuron. So what our basic neuron has? Basic neuron has the activation function and a bias.
Yes.
And activation, each neuron has the activation function. So we are telling in ANN we'll use ReLU as the activation function. Bias can be simple, B1, B2, B3. These are all simple neuron. But to solve the vanishing problem, vanishing gradient and exploding gradient problem in case of RNNs, what we do? We replace neurons with a special cell. A special cell, specially designed cell. We replace the concept of neuron itself is different. We take a special cell which is called Lstm cell or GRU cell. These are two different kind of cells, Lstm and GRU. So these we replace our neurons with Lstms and GRU cells. So if you are using 3 neurons instead of 3 neurons, we'll use 3 Lstm cells. So what are these Lstm cells? That is the main topic of today's discussion. You just wait for 5-10 minutes, it will come to you.
Okay.
Now, vanishing gradient, I think we have explained in detail. Now you go for exploding gradient. Now, for vanishing gradient, I said when you calculated the derivative of that loss function with help of W1 weight with respect to W, it was less than 1. Now, assume reverse, like it was, you calculate the same derivative of loss function with the help of W1, but this time it is more than 1, say 1.25. And same weight matrix, and you are doing back propagation now. Fourth layer to third layer to second layer to first layer, and then to input layer. Okay. So you are doing same. Now 1.25 in between some weights may have higher values. Weights may have higher values because we don't have any control on that. The weights may have higher positive values. So now 1.25, if I multiply with a number more than 1, it will get further multiplied. I go from one layer to other, one more layer back, it will get further multiplied. It will get further multiplied. If your network is very deep, in case of this, it happens in the case of very long sequences, as it happens in the case of very long sequences. If your network is deep, then you have so many layers, uncountable layers. It will never, number will explode beyond your computer memory. So that is why, that is computational aspect. But what will be the effect in our what will be the it is similar to if your number explode, what will happen? Your neural network will become unstable. It will be, you will be unable to, in vanishing gradient it becomes zero, near to zero. So trending doesn't happen. Now here reverse happens. Here your number becomes so large that your network itself becomes unstable. So still trending doesn't happen. You are not able to train. So in both cases, vanishing and exploding gradients, you are not able to train the network, and both are the same coin, they are different sides. So this is one side of the coin, this is other side of the coin. One you call as vanishing gradient, other you call as exploding gradient. Both caused because of long sequences. And what happens is if sequences are long, your networks are long. They are having more layers. So for long sequences, exploding gradients and vanishing gradients, opposite phenomena, but they cause the same thing. And the reason is the same. Understood? So to solve this problem, we go for something called LSTMs. Okay, there is some specially designed. This problem was very acute initial years for like I want to search when LSTM was invented. Just give me a minute. I want to check when LSTM was invented. So LSTM 1997. See, it is not very old also. So LSTM was invented in 1997. And it is given by one German scientist actually. It is a German paper originated from Germany. So before 1997 also, 30 year before that also neural networks were there. Because I remember one of my friend Anup Parki, one of my friends, he sometimes comes to take our classes. He was there in MTech in 1992, IIT Bombay. So that time also in their course, neural networks were there, 1992. Neural networks were there, and before that also neural networks were there. So that's very much neural networks are very. But before 1999, this problem of vanishing gradient, 1997, sorry, before 1997, the problem of exploding gradients and vanishing gradient was not able to, unsolvable. People were not able to solve it. It looks easy, but people were not able to train long networks, big networks, because of the vanishing and exploding gradients. Okay. So 1997, a big breakthrough paper came, which is LSTM. It is originated from Germany. Okay, and after 1997, a lot of progress has happened in this field, and recently, I will tell you one more variation, less wet variation of LSTM has come, which is called GRU. So GRU, just a minute. GRU was invented in 2014. See, we are going to read GRU today. So LSTM is 1997 development, and GRU is 2014. And Chao, this time GRU I think developed by some Chinese origin person named Chao, some Kyugyun Chao. I think looks like some Chinese person. I'm not sure, but name reads like Chinese. So Chinese or Korean, some Chinese or Korean person invented. So GRU. So GRU is nothing but a lightweight version of LSTM, which is invented as recently as you see, 2014. So 14 is not very long, only 6-7 years back. So these are very acute problems, vanishing and exploding gradients. So first solution was given in 1997 by German scientists. So now we'll straightaway like this bidirectional RNNs. I think we have already covered yesterday in detail. So I don't think I need to cover it today. So I will not cover bidirectional RNN. So we'll straightaway jump into our LSTM. So LSTM as a coding concept, RNN and LSTM, there is no difference. Just like our linear regression, now we import linear regression function, and when we have to use L1, L2 regularization, then either we import TASO or RITs. Same thing here. When you have to use RNN, we import RNN function, use it the same way. And when we have to use LSTM, there is no change. Just import LSTM function using the exact same way. So coding is no different. But concept, there is a sea change. Concept, there is a sea change. There is a big difference. And there is lot of theory involved in LSTM. And I would say it is a bit complex also. So be little attentive. And even if you don't understand today, I think a couple of more reads or couple of videos, if you see, then I think you will become, with time, you will become familiar. So it's a new concept today. So be a little more attentive. Okay. So now I'm starting here with a Lstm concept. First of all, I want you to spend some time on, I'm removing my video. Okay. So I have put it on the bottom most. I want you to take a minute and spend some time on what is given in this particular, because it is too much filled up slide. So I want you to have a look where what is written. Then we'll understand it. Understanding is 5-minute job. But I want you to see where what is written first. I spend 1 minute, 2 minutes to understand, read where what is written. Have a look, spend 1 or 2 minutes. I will join you in a second. Okay. Just spend 1 or 2 minutes on that. Yeah, sorry guys, I'm back. So I think you had a look, comfortable look. तो इसको बोलते हैं ना जी भर के देख लो, तो देख लिया आप लोगों ने लगता है. So now first of all, whatever that colorful image you are seeing in between of that PPT, this is nothing but a neuron. Neuron means neuron, the neuron of our actual NN or this we are replacing by this cell. So see, it is complicated. Okay, it is doing a lot of things. It is doing a lot of things, but it is a single neuron-like structure. So we call it as a Lstm cell. So now see what it is doing. First, note the 3 gates. So can anybody read out for me what are these 3 gates which are there in that?
One is the input gate XT.
No. Gates I have written in the. I have written in balloons those 3 gates.
Forget gate, input gate, and output gate.
Okay. Now on the bottommost side, bottom corner, bottom left hand corner, you see one input as XT and HT minus 1. So can anybody explain what is XT and what is HT minus 1?
XT is the input.
Input feature, right? What is HT minus 1?
HT minus 1 is from the previous sequence.
From the previous network, whatever input we are getting, that is HT minus 1.
Yeah.
XT is our current time step input. Now you see the output here. Output. The right hand, bottom right hand side. So there is HT. What is HT?
This is the one that is going to be fed into the next.
So this HT is nothing but output of this cell, right?
Yeah, output of this.
That will feed into next cell.
Yeah.
Okay. T plus 1 cell will take this as an input. And there is something in green which below it is noted as current output. So what is the current output?
Output of correspond to extreme desired output.
Desired output, yes. It is out. It is assume it is many to many. So it is one of the output. This is the output of this time step. So we are right now in the time step T. So output of time step T is what I have denoted in green as current output. Now there is something you see this cell on the top right. Top right there is cell state CT. I'll explain it what it is. Cell state CT. It is something new actually. We not discussed earlier. So can anybody read what is written above CT? There is text. There is a bullet point and a text I have given there. Can anybody read what is it?
Yeah. Are you asking about the output gate, sir?
No, not output. Above CT cell state, there is a bullet point. There is a bullet point. Can you read out?
Information or context over longer discrete steps up to hundreds.
Okay. So it is context. Understood, na? So all translation, as we discussed yesterday also, whatever translation or job we do, there is a context involved in it. Okay. Context means input from previous steps, right? So that context is nothing but context is city, cell state. So that is context. Context is carried over by this city. Now you assume how you see the vertical top line, black line. CT, cell state, corresponding to cell state, there is a vertical arrow, vertical line with a arrow. Okay, vertical line, top line, vertical line with a arrow. In between there is a cross. After that there is a plus. Can you notice that?
Yes.
You notice that, right? There is a cross and there is a plus. Malin, do you note that?
Yes, sir. Yes.
Okay, now what is city? City is nothing but input coming, context input that is coming from previous networks, previous timestamp. Okay, so now with this line, I would say that we have a facility to give a clear passage to that input which is coming from previous timestamp. Suppose this cross and plus doesn't do anything. Suppose this cross and plus doesn't do anything. Whatever input I am giving from the previous time step, as it is, it can pass through the neuron. So as if neuron is not there. As if neuron is not there. So whatever context input I am getting from previous time step, it can be passed as it is without any processing. Is it understood?
Sir, can I try?
Yeah, please.
To put an example here, maybe we'll be able to understand.
Example.
There was a sentence in your previous the cats found a lot of fish. They were very happy, something like that. So
here.
Yeah.
Where is that cat wala?
I think it was Vanishing Gradient. Yeah.
Those
cats caught a fish. They were very happy. So if we were to think of this, then those cats caught, all that will be xt minus 1, whatever. Now context would be cats and will be cats and fish, right? Is that correct? So the forget get will have to take out those caught and all that. Cats and fish, it would have to retain and send it across as context.
Yes, exactly. Yeah. Okay. So this very happy, which is there in the end, has actually context of cat and fish. Okay. So when a cat catches a fish, it is very happy. That's how it's the context. Yeah. So this context, cat, fish, it is coming from the long back sequence, long time step back. Okay. Maybe say t minus 20 it is coming. So it has to remember that. Okay. So that is how it is. Thanks, madam, for this example. So this whatever context is coming from previous time steps, we can allow it to pass without any processing through this particular cell. That's what this line is meant for, without processing. But sometimes we allow it to pass without processing, sometimes we do a little processing. So this processing is cross and plus. So cross is element-wise multiplication. Element-wise multiplication. Element-wise multiplication, you understand. Like if two matrices are there, one matrix is 3 by 3, one row there are 3 elements. And another row also there are 3 elements. Row matrix, you assume a row matrix. One row there are number 10, 20, 30. And another matrix is there 40, 50, 60. So 10, 20, 30 is one matrix. And 20, 30, 40, 60 is another matrix. So by element multiplication, element-wise multiplication we means 10 into 30, 10 into 30, 20 into 40, and 10 into 40. 10 into 40, okay, let me write down. So one matrix is 10, 20, 30. Other is 40, 50, and 60. So element multiplication means element by element multiplication. 10 into 40, 20 into 50, and 30 into 60. Understood? Element by multiplication. This plus means it is a vector addition. So there are some input coming to this particular cell state, which is the path, that horizontal black path which is there. There are some inputs coming to it from bottom, which we'll read it now. So from inputs are coming. At the stage where cross is mentioned, we do element-wise multiplication with those inputs. And where plus is written, we do simple vector addition, element by element addition, vector addition. So this is about cell state. So cell state means any context input which is coming from previous time step, it can pass through without processing or with little processing. It depends on how the network behaves, how networks want it to. If network want it to pass without any processing, it can pass without processing. And if network wants us to do a bit of processing, then we do processing at two places. At cross we do network element-wise multiplication, and at plus we do addition, vector addition. Okay, so this is very simple now. Now let us study our first gate. First gate is nothing, forget gate. First gate is forget gate, right? Forget gate. So for forget gate, below this diagram, I have given one bullet for forget gate. Can anybody please read that forget gate?
The forget gate determines which relevant information from the prior steps is needed.
Okay, understood now? Forget gate forget gate means what is to be remembered and what is to be discarded. That's what it decides. What is to be remembered? What is to be remembered means HT and XT. Inputs are combined. HT means input coming from previous time step, and XT is your new feature. Both are to be added up, and this addition we pass through a sigmoid function. You see that red S is there, res white S inside a red box. So that is nothing but a sigmoid function. So that HT means input coming from the previous time step and the new feature XT. We combine them and we pass it through a sigmoid function. So that is your simple forget gate. So can you tell how it is, what it does sigmoid? If I apply a sigmoid activation to HT minus 1 plus XT, for HT minus 1 plus XT, if I applied a sigmoid activation, what will happen to it? Can anybody tell from previous experience? I am applying a sigmoid activation to HT minus 1 plus XT. I am applying a sigmoid activation. So what will happen?
It will be either 1 or 0.
That you are going to extremes. So there can be something in between also, right?
Yeah. Right.
So I think you're correct. You have rightly replied. Sigmoid function has a minimum value of 0, maximum value of 1. And in between there are fractional outputs, 0.1, 0.2, 0.7, 0.8, like that. So sigmoid function, if I apply sigmoid activation to input, so HT minus 1 is a part of input and XT also input. So HT minus 1 coming here and XT coming here, which is the current feature. I add it up and apply a sigmoid input. That means a fraction of that only will pass up to the cell state. Understood now? Sigmoid function will apply a fraction. Either 0 means nothing will pass, 1 means full will pass, and if a fraction is applied 0.4, 0.5, 0.6, a fraction of that will be passed. So understood why it is a forget gate?
Yes, sir, kind of, yeah.
Why kind of, madam? You discuss 5 minutes more. I have time and give you time.
No, I understood. But then if there is a way where I can actually see an example and see
You
what
will
is
never be able. I'm sorry, you will never be able to see any example. In inner working of Lstm, nobody can. Is not explained actually.
Oh, okay.
And you will not get any article, video which will explain you that. Maybe this animated explanation which I have given you, one link I have given animated. So this is the animated link which you can see later.
Okay.
This example is given here, illustrated guide to LSTMs and JRE step-by-step explanation.
Yeah.
So this is nothing but an animated explanation that will the closest you will get.
Okay.
And nothing beyond that. So you have to imagine. So whatever input I am giving you, which is HT, which is coming horizontally, and XT, which is the feature vertically. I'm combining them and passing through a sigmoid function. Sigmoid function means either nothing will pass if it is 0, 1 means all pass, all input will go exited to cell state, or a fraction of that will be passed. So it is for forget gate, right? It is a forget gate. It is returning something, it is passing only some information to pass. It is allowing only some information to pass, and information is passing where? It is passing to cell state. And when it passes to cell state, we do a element-wise multiplication with the context information. Whatever context information is coming in the cell state means that horizontal bus. Horizontal bus you see na here, horizontal bus. So the horizontal bus is nothing but cell state, which is input coming from previous time step. It is nothing but a vector. So that is cell state bus. Bus matlab same bus as your city bus. So it is a bus which is carrying cell state vector. It is carrying that vector. So with that vector, we'll apply whatever input is going from forget gate. We do element-wise multiplication. So that's where first processing happens to cell state. First processing. Then we come to input gate. Now in input gate, there are two rounds you see. One round is your sigmoid, red one is sigmoid, and blue one is 10H. So can anybody tell me what is the maximum and minimum value of 10H?
-1 to +1.
-1 to +1, right? So these are two extreme values, and in between it can take any fraction, either minus fraction or plus fraction, right? So now same input like ht-1 and xt, as you see from the diagram, yellow anda, yellow egg you see in between, yellow egg. I marked it with a yellow egg. So ht-1 and xt, it goes to first the red ball, which is nothing but a sigmoid function. So sigmoid function works, it passes a fraction, it takes a fraction of it and passes ahead. Same thing, ht-1 and xt then passes through the blue ball. So blue ball is nothing but your 10H. So 10H is called modulator. So 10H is a modulator. What 10H will do when you multiply ht-1 plus xt by 10H, what will happen? Can anybody tell?
It will be the same value with either plus or minus.
Yeah, it will assign a sign to it.
Yeah.
Sign means minus means reduced and plus means increase, right?
Yeah.
So now this fraction which is coming from red ball is combined with the 10H modulator, which is assigning a sign to it, either minus or plus. Plus means it is signaling it to go up, and minus means it is signaling it to go down. So it is nothing but a moderator. We call it as a modulator. If you have studied electronics and all that, mechanical guys, it will be difficult, but electronics, it is some modulator is there in many circuits. So it is a modulator. Modulator means nothing but a regulator. Either it brings down or brings up. So that is combined. Then is input coming from sigmoid function and 10H function is done element-wise multiplication. They are combined. Sigmoid input and 10H input. Right now we are talking only about input gate. So one input is coming from sigmoid and one is coming from 10H. Element-wise multiplication is done. So 10H is assigning sign to whatever sigmoid input is coming. After that element multiplication, it is passed on to the cell state. So cell state previously one cross we did with forget gate, we did one processing which is cross. I told you forget gate. Whatever is coming, then we are giving a vector addition. Vector addition we are doing whatever is coming from input gate. Dr. Shailesh, is this understood?
Yeah, that I am understanding, but my question is
you will things will be clear. Right now we are in the middle, so you ask question at the end.
Yeah.
You right now understand what is happening.
Right.
Okay, just understand what is happening. So now you understood cell state. Now you understood forget gate. You understood input gate. Why input gate? Why it is called input gate? Because sigmoid is fractioning it, like it is allowing only something to pass, and 10H is giving a direction and fraction to it. It is taking fraction also and it is giving direction also, plus or minus. So that is it is the input processing. That's why it is input gate, and it is finally added up to cell state. Then final comes is your output gate, which is in orange anda. Orange egg is there. You concentrate on that. Now there also you see one red ball and one blue ball. One red ball and blue ball. Okay. So red ball is again your sigmoid. So sigmoid means it is direct ht minus 1 and xt is coming to this red ball. Again we are taking a sigmoid fraction of it, and then whatever cell state there is from cell state we are drawing an input down. From cell state we are drawing an input down, applying 10s to it, and then doing an element wise multiplication with sigmoid. This is element, and that whatever is there, this is the output. So this output is getting passed that two things. HT means your what is to be passed on to the next time step, and what is your current output that is getting passed on to that. This is the whole functioning of your Lstm cell, and it is, mind it is just one neuron. Okay, it is just equivalent to one neuron. So how complicated it is, and at every stage where we are doing a sigmoid and all those things, we have weights associated. So Lstm is very heavy, computationally very heavy compared to a neuron or anything. So it requires a lot of computational resources. Understood? Because any stage you go, every stage there is a vector, in between vector is involved. Weight matrix is involved. Weight matrix multiplications are happening, additions are happening. And there are so many weight matrices that even if I want to count, then I may have a difficult time. So it is very complex, very computationally complex. I just explain you this in detail so that when you coding wise there is nothing. All is done by computer. Of course, all done by computer only. But you should understand actually, because we are all technocrats and senior people, so we should understand what is the technology behind it. So this is in detail. You have functioning of a Lstm cell. You have inputs ht minus 1 and xt. Then you have output ht and current state, and then context information ct also gets out either with some processing or without processing. Ct can pass on. So this ct means what? All your context which is there coming from the back, if you are not processing it or reducing it, it can just be passed on to the next layer without processing. So long sequences can be remembered. CT is your context, right? Context from the back sequences. So it can pass down without processing, reducing or enlarging. So that's what makes Lstm cell process very long cells, because at some stages your CT may just pass without any processing, just as it is coming, just like that it is without any weight matrix multiplication, it is passed on to the set cell. Okay, so that is how, because of CT, remembering long and small long sequences is possible. Then you have three gates: forget gate, input gate, and output gate. Now, I want you to switch off your mind. Don't get into details. This detail is okay. Even if you are not understood, we can discuss it later. Don't get into detail now. Now you come up, say 10 levels up, and read only these three bullets. So can anybody read these three bullets? I want you to, in totality, I want you to understand what a forget gate does, what a input gate does, and what a output gate does. Because there are only three gates in this particular Lstm cell. What each gate does, you should know that. Processing is okay. Internal processing is good to know. But what each gate does, it is must to know. So can anybody read these three bullets below this diagram? Forget gate. Can start with forget gate.
Yeah. The forget gate determines which relevant information from the prior step is needed.
Right. So forget gate, simple job. Keep some and allow to pass something. It will keep some, it will discard something, and only important information it will allow to pass. So that is forget gate. Name itself suggests something it will forget and something it will allow to pass. Then output input gate. Yeah.
So the input gate decides what relevant information can be added from the current step.
Yeah. So from previous step, we decided with the help of forget get what is to be retained. That is forget get does. After that, you have to add the current input also, no, which is ht minus 1 and xt, which is current input, you have to add there, right? So that we add in that processing we do in input gate. And what about the finally output gate?
And the output gate finalizes the next return state and the current
output. That's all. And if you think whatever I have explained to you, you have to give it a thought once it is over. Maybe you have to listen video second time, or maybe some other author's video you have to listen. Now you should be able to relate how a forget get works, simple sigmoid function, how a input get function. It will simple sigmoid and a 10H. 10H is nothing but your modulator, and sigmoid is nothing but a fraction of input which it remembers, and then how a output get works and how the cell state works. All this is explained to you in detail. I think more than this detail you don't need. And that's what you can get in any theory book also. If you read it in theory books, it will be explained in 5 to 7 full pages. You will get lost. So I never, for LSTM and all, I always prefer to listen to videos rather than reading books. Because book reading so much of text is very, and it's a real complex concept. It's not easy. So whatever you have learned so right now, it is just first time getting into your head. So a couple of times you have to listen to video, see some more other authors, some other instructors video, and if you are very keen at, then write some book, read some book. Then after 2-3 times it will be very crystal clear to you, so that you also will be able to explain it to others. But concepts are very simple. There are only two things. One is sigmoid and one is 10H. 10H gives either up, down sign to it, up, down sign. That is nothing but a modulator. And sigmoid is a fraction, it gives a fraction. What to pass and what to forget. These are only two basic functions. And apart from that, there are two mathematical concepts as vector addition and element-wise multiplication. So if you remember these things, individually see each gate, forget gate, output gate and output. Individually, don't jumble up. Individually see one by one. Then you will be able to analyze it very easily. Even it took time for me also to reach to this level. I'm talking to you today also, right from morning 7 o'clock, 7:30 to say up to 2 o'clock. I was working on this only, just to explain you properly. I was working on this. That's why I'm able to explain you so easily and freely. But don't assume that I have not put efforts. It's really effort. You need to put some effort to fully comprehend it. So I think for now it is okay. Don't get worried. Just do it couple of more times, different sources. Okay. So this is what the main concept of LSTM cell. And now just I want somebody to tell how LSTM cell is able to remember long states, long dependencies. Because of what?
Because of the cell state CT?
Yeah, cell state CT. Yeah, that's what makes us remember long state. And cell state, there is a beauty. Either cell state, you allow to, like if cross and if cross there is coming 1. Element 1 multiplication if it is coming 1. And this vector addition if it is coming 0. Then cell state will pass as it is without any processing. So without any processing pass means vanishing gradient also will not be there and exploding gradient also will not be there. So that problem is solved. But computationally it is super heavy. Because at every stage you have weight, you have associated weight where you multiply like input and like ht minus 1 and in ht minus 1 which is coming and ht plus coming, the simple ht. Then in between sigmoid and that you have weight place. There is a weight matrix which you have to multiply. So we are not getting into that much detail. But at every stage, you assume there is a weight matrix multiplication is there. So it is very super heavy compared to our neurons, simple neurons. So so this was invented in 1997. So guys, scientists were struggling how to simplify it, how to make it faster and all those things. So finally, 2014, one person came with another solution which is called gated recurrent unit, GRU. gated recurrent units. So that's another 10 minutes we'll discuss, and then we will close it today. So these in between to change your like just change of taste. I'm giving you this particular example here. Lstm for video captioning. So videos are video sequences fed from the top, and it is doing captioning. Captioning means it is titling it, subtitling. So this person is on the phone. So a man is talking. So that is maybe on the mobile phone. A man is talking on the mobile phone. That would be more correct. So that output is being given by the neural network, and input is the video frames. So a man is talking on the mobile phone. That is the output. So this is, you see how what kind of structure you have. So instead of RNNs now, we are using LSTMs. So in practice, nobody uses RNN because of this vanishing exploding problem, gradient problem. Nobody uses RNN. If anybody tells you use RNN, means by default either it is LSTM or GRE. Nobody will use RNN. By default, either you have to use LSTM or GRE. Means understand that thing. Nobody, though the procedures are there to use RNN also. Short sequence, a man saw a cat. So the movie was good, whether it is positive or negative. Only a movie was good. A movie was good. Only 4 words. 4 words. So like that, small you can use RNN. But in practical scenarios, use of RNN is very limited. So if anybody tells you use RNN, you need not even ask. Either use LSTM or GRE. Okay. So this, I think, have a look at 1 minute. I will have a water in between. So just encoder, decoder, you note encoder at the bottom and decoder at the like that. So if you notice it, it's a encoder decoder architecture with the help of LSTM. Okay, so I think in great detail today we have discussed LSTM. And if you read any more articles or see any more videos, things will be very easy for you now. That should be easy, at least that's what I expect. So now let us see, for you I have given a lot of material in this, which we need not go. So see, there is another presentation, more simpler presentation of LSTM. Then simple, these you can read on your own. See, cell state. So I have compared cell state with a conveyor belt. I just copied this conveyor belt concept from internet and pasted this particular text on that. So cell state is just like a conveyor. So these boxes are nothing but context vector. Context information means context vector which is coming from previous states, previous time step. So it just takes that and passes it to the next step. And here, as it happens in the conveyor also, there may be one laborer standing here. He may put some label on that, label on each of these boxes, or he may remove 1 or 2 boxes. Like that, some processing happens. So like that, we have 2 times processing in the cell state also. One is element-wise multiplication, and one is vector addition. So simple processing means some person is keeping putting labels in between. There are 2 laborers are standing. One laborer is putting one label, one laborer is putting other label, and at the end, finished box is taken up for stocking in your supermarket. And it will be taken to supermarket. Maybe label 1, label 2 will be pasted like that. That is the processing. That's what happened in cell state also. So I think this all you can have a look. I don't think we need it. See, sigmoid and all. Forget layer I have explained in like a lot of details I have explained, but I think all we have covered. So when you have say 10H, and I have included 10H sigmoid here, input layer. Then output layer also separate CT is there, and if you are very much interested, you have equations as well. So we are not discussing these equations of LSTM here, but for academic interest, if you are interested, I think you can very much go through these equations. And if you are interested, we can discuss in some other class. You just go through this equation. It will be easy now for you. It is just like feed forward here. It is feed forward. So very simple. You just assume what sigmoid. Sigmoid. This sigma is nothing but sigmoid, and 10h they have represented as 10h only. Element wise multiplication also given by star. Addition given by plus. So it is all simple, same thing which we have discussed, expressed in mathematical form. But if you can explain it to somebody in this format, he will never ask you any other question about deep learning. Mind it. If anybody asks you what is LSTM and you explain in this format, you will clear interview for sure, number one. And in his life, he will not ask you any other question about deep learning. So that's what is in some other pictures also I have taken. See here, it is another representation of same forget gate, input gate, logic cell state. So different equations are given. So all material for you, you need not look outside of it. Just look into it. So as a LSTM conclusion, I'm reading this last slide. Forget gate determines which relevant information from the prior steps is needed. Malin madam, can you read it? Your reading is better.
Sure, sir. Yeah, the input gate decides what relevant information can be added from the current step, and the output gates finalize the next hidden state.
Yeah. And forget gate?
The forget gate determines which relevant information from the prior steps is needed.
And I'll tell you, like one or two more viewpoints you need. Like I might have left couple of things like why there are two inputs here, CT1 minus 1, and why CT minus 1 and HT minus 1. These two inputs are here to this cell. And how this CT and HT, which are output, CT and HT, how they are getting used. So that's where you need some more more detailed understanding of LSTM. Try to search actually. I couldn't get much on this. Everyone tells CT minus 1 and HT minus 1 are the inputs. But how CT minus 1 coming separately, HT minus 1 coming separately, and how to use CT and HT, how we can use the CT output and HT output, which is there. How to use it.
What I thought from whatever I have understood so far is HT minus 1 is from the immediate previous sequence.
Okay.
But CT minus 1 would be a collection of all the contexts so far.
Yeah, that's right. Yeah. So that is the context information flowing from the all previous time steps. And HT minus 1 is nothing but your immediate previous time step. HT is your immediate output. CT is the context output. So immediate output you have to see in the terms of context output. So both we have to combinedly you have to see context vector and immediate vector. So that's how it is. And with time, I think it will be more clear. So now we get to our next 10 minutes of our today's lecture.